Do you like to work with metal, fire, electricity? Would you like to make money doing it? At Southwestern, we can help make your dream a reality. With our degree and certificate programs in welding, you'll be prepared for a career in the welding and fabrication industry in as little as a year. Check out our website and let Southwestern spark your career in welding today.
This is Southwestern's dental assisting program. In just one short year, you could be a dental assistant. Sign up now for your one-year dental assisting certification.
There we go. Hi, my name is Ron Metzger, and I've been teaching geology at Southwestern Community College for the last couple of years. It's an exciting time to be teaching in the health and science labs at SWOCC as we work towards funding a new health and science facility at the college. Toledo Hall is the building I work in, and it houses our science labs. It was constructed in 1965, so the labs have undergone relatively little updating since that time. Over the years, the faculty have provided an exceptional foundation in the lab sciences. It's relatively easy to see how an investment in the health side of the facility will pay dividends in our local communities. The added lab and class space will allow additional cohorts of nursing students in new programs. This will allow our local residents to go through the programs in our family wage jobs, Bay Area Hospital, all of our other local providers. As we look forward, it'll be interesting to see what we accomplish as a college community with lab facilities and equipment equal to the task of teaching in the 21st century. I hope you will work with me as we move forward with this project. So, thank you all for being here tonight, because I know there's only about 12 other things going on around town currently, and another 8 that were earlier in the day. In the event that you didn't sign one of these handy-dandy little sheets, if you could just take a second when you leave to go ahead and do that. Helps us justify bringing in speakers, and a few of the speaker bureaus kind of request an audience of 200, and when you tell them you live in a town under 30,000, if you combine Coos Bay, North Bend, they kind of go, yeah, right. So we all know that we get 200 to 300 a time, but in the big city, they don't always recognize that. Also, if you have a place to post the final talk in the academic year, we've got Josh Roaring coming over from the U of O. He's going to be talking about some Cascadia-related events. So there's some big posters, there's some little posters out there. If you have a place that would post posters, I'd be glad to have you take some of those with you tonight. And also, I didn't bring a prop with me, but there's a couple books out there. If you came here looking for a copy of King of Fish, I made a mistake and I didn't bring a couple of my extra copies with me, because apparently I might have been able to sell them along with Rocks Don't Lie. But that said, Dave did bring a couple copies of Dirt 1 as well as Growing a Revolution that he's going to be talking about tonight, and also some copies of another book that he wrote with his wife, Anne, about hidden nature. So those will be available in the lobby afterwards, as well as a huge thank you to the master gardeners, to the Coquel tribe, to Coos Watershed and South Slough. Most of those folks have been at a number of these events and providing information to all of us about how they relate to some of the topics that have been present in the series in the last few years. If you happen to have a cell phone with you, please turn it off or into airplane mode. That would be a bonus. I'll double check mine when I look here in a second too. It's really a thrill to bring Dave Montgomery back. And as we were driving over from Eugene Airport late this afternoon, one of the things that the discussion involved was where he's been talking about this particular topic. And it's essentially globally. And he just spent several days in Idaho and Colorado, at a variety of places from 80 degrees to minus 80 degrees, all kinds of wonderful places. And the most comparative that I could get was Coos Bay and Stockholm, Sweden, because he left Seattle this morning, and I picked him up, and he's heading back to Seattle tomorrow. And what he said was he left Seattle, flew to Stockholm, gave a talk, jumped back on a plane, and flew back to Seattle. So as far as I can tell, we are exactly the same as Stockholm. Well, the first talk that Dave gave, he had just written the book Dirt, Erosion of Civilization. And I was out fishing with my buddy Don Ivy, and I was counting boats. And I got up to 250, maybe 300. And I thought to myself, why am I having this guy come talk about dirt when he's got to talk about the salmon runs for the last 1,000 years? So he came down and did that. Then he came a few years later and talked about a geologist's viewpoints of Noah's flood and basically a little bit of time and things like that. And as we were sitting around talking, he said, yeah, I'm working on a book that I'm affectionately calling in the moment Dirt 2, which is growing a revolution. And so I said, well, you know, we missed dirt the first time. Maybe when you get that one done, you can come back. And so he's graciously made time in a crazy schedule to come down. Before I forget, I want to thank IT, because while the flights were all fantastic, the tech and getting the Mac to work, not so fantastic. So thank you guys for doing a great job in making this happen. Also, thanks to DB Western for funding, as well as the Mill Casino and the Southwestern Foundation. And you already saw about the health science building. There's not much that you can say about Dave that you haven't already seen in some of the posters and some of the other commentary. He's one of the country's leading scientists and leading authors and speakers, and has a knack at getting information out in a way that everybody can understand it, whether it's by the spoken word or whether it's in print. So it's really my pleasure this evening to introduce Dave Montgomery.
Great. Ron, thank you, and thank you for the invitation to come back to Coos Bay. What he didn't mention is I actually did some of my PhD research on Mettman Ridge 30 years ago on the other side of the bay. But what I'm going to talk about tonight is what my wife Ann Baclay and I affectionately refer to as our Dirt Trilogy now. Because 10 years ago when Dirt 1 came out, I never would have imagined that a decade later I would have written 2 more books about soil. So I'm going to try and take you through the sort of the thought process and the evolution of my own thinking and Ann's thinking about soil as we worked through these 3 books. Because I'm a geologist and she's a biologist. And that first book over there, Dirt, the Erosion of Civilizations, is the one that you might imagine that a geologist might write. It looks backwards through history. It's about the role of how people treated land in the fate and course of civilizations since the dawn of agriculture. It effectively defines what the problem is with soil degradation. That book in the middle, the one that Ann wrote with me, The Hidden Half of Nature, was our exploration of trying to figure out, okay, well, what is it that actually really controls and influences soil fertility in ways that we weren't necessarily taught in graduate school in our soil science classes. It's the one class that she and I took together at Berkeley. And it turns out, well, I'll explain sort of our thought process and how we go through that, but it is really looking at the important role of microbial life, bacteria and fungi in the soil, on soil fertility, and then it also turns to look at the role of those same kinds of organisms and those communities of beneficial organisms in the human gut and the parallels there. And that third one, the one on the right, Growing a Revolution, the new book, Dirt 2, as Ron was calling it, and that, as I apparently called it a while back when I was first thinking about it, takes those ideas that were developed in the first 2 books, and it's a standalone book, but it goes and looks at how the prognosis for restoring soil fertility on farms around the world is. Can we actually fix the problems identified in that first book using some of the methods identified in the second book? So I'm going to give you the overview of our Dirt Trilogy, but why would a geologist be very concerned about the problem of soil degradation and land degradation, concerned enough to actually spend nights and weekends for 10 years writing books about this? And this map, this global map of soil degradation from the United Nations from a few years back, really sort of tells the story of why. You'll notice that there's a lot of orange and yellow on that map, areas where the land is either very degraded or has been degraded. And by the land, we mean agricultural land in this case, is what they were censusing. And while you could, as a scientist, you could pick nits with some of the methods that went into making this map, it presents a fairly dire global picture. There's an awful lot of degraded land in the world. But I also like to use this map to make the point that if you go within any of those red zones on the map, you can find individual farms that are turning around the pattern that you would take away from this. There's farms all around the world in each of those red zones, in other words, that are building fertile soil at a pace faster than nature actually makes it. And so what I'm going to do in this talk is take you through sort of the depressing story of how we generated this map at a global scale in the first place, and then try and turn it around into an optimistic story about how we can completely reverse the pattern at a global scale. Well, what about, this is a map, what about numbers in terms of the magnitude of soil degradation around the world? Well, there was a paper that David Pimental and his colleagues at Cornell University wrote back in the 1990s that tried to census how much of the world's agricultural land had been degraded in the time after the Second World War. And you could think of this as sort of up to the end of the 20th century. And what they came up with was that some 430 million hectares of farmland had been abandoned by the end of the 20th century, land that was once in agricultural production, but that was no longer used for growing food. So 430 million hectares is kind of an arbitrarily large number, right? When you get into the millions and billions of things, it all kind of gets fuzzy to me. It's an area the size of China and India combined that we used to grow food on, but that is no longer being grown, no longer being used agriculturally around the world. That's about 1/3 of all the present cropland in the world. In other words, since the end of the last ice age, we've degraded about 1/3 of the land that we might be able to use to feed people. That's not a good prognosis for the 21st century when we expect the human population to head up to somewhere near 10 or 11 billion people by the end of it. Well, so have we solved the problem of land degradation? The most recent report that I can find that addressed this at a global scale dates back to 2015, so it's just a couple years old. That was another UN report, the Global State of the Soil Assessment, and they reported that humanity is losing 0.3% of our agricultural production capacity each and every year due to the degradation of soils and the erosion of soils. 0.3%. Kind of a small number, right? I mean, on an annual basis. It's kind of what we're probably all getting for our savings accounts in terms of an interest now. And it's kind of hard to see that rack up over time. But if you think like a geologist, that 0.3% over the next 100 years is going to translate into another third, 30%, roughly 1/3, of the world's agricultural production capacity if we maintain the course that we're on in terms of land degradation. I don't think we will maintain the course we're on, so I'm not arguing that we will be down to just 1/3 of the world's agricultural production capacity by the end of the 21st century, but I am going to argue that agriculture is going to need to change this century if we're to avoid that. And that's where the optimistic part comes in by the end of the talk, because I think we actually can. I think there's brilliant examples of people who are already doing it around the world. There's just not enough of them yet, but we'll get back to that. So this is not just a problem of ancient history, but there's a lot of really good ancient history that looks into the issues of global land degradation. And I tried to synthesize as much of that as I could find in writing the Dirt Book, going into the story of societies around the world and how they had treated their land. And what I came up with was a very similar pattern of land degradation due to soil erosion and degradation, and its role in the demise of ancient civilizations, starting back actually in Mesopotamia, some of the earliest Western agricultural systems, but also in Neolithic Europe or Bronze Age Europe, Rome, the classical Greece, the southern United States, Central America. There's a lot more examples that I went through. And this idea that land degradation and soil erosion influenced ancient society is not a particularly new idea. I'm not claiming credit for having thought this up. There's books that actually, it turns out, date back to the 3rd, 4th century BC that addressed this, because Plato talked about it in classical Greece. But if you look at most environmental history textbooks today, what you find is the argument that it was deforestation that caused the erosion that led to the undermining of ancient civilizations. And I actually did some of my PhD research looking at the erosive effects of clear cutting on steep slopes in your guys' backyard around here. And you can document that if you clear cut on very steep slopes, you get more landslides. That science is pretty settled. But it's not enough if you crunch the numbers to explain the wholesale loss of the soil across a whole region, like we can document in regions of the ancient world, or the old world, or in regions around the world. So the idea that deforestation could cause the soil erosion and undermine ancient societies just did not sit right with me, because the numbers didn't seem to pencil out. So what was the problem? That's what I looked into in writing the dirt book. And it turns out that the villain of that book, if a nonfiction book can have a villain, was not the axe, it was the plow that followed. It was the farming practices that maintained the soil, maintained the land in a state of easy erodibility, of vulnerability to wind and rain, that set the stage for the wholesale loss of the soil across regions that I'll talk about briefly in a couple minutes. And what was the mechanism? Well, what does a plow do? When you plow, it turns the surface of the earth over. It gives you a blank slate to plant into. It can be used to prepare a planting bed. It's been popular for millennia because it's a really good method of weed control. But before the next crop grows, or those weeds grow back, the land is sitting there vulnerable to the erosive effects of wind or rain. And if you think about soil the way a geologist thinks about soil, as a system that's made from the breakdown of rocks and the merging of those mineral elements with organic matter, both living things and once living things. Biology, the living and the dead. It's that merging of geology and biology that makes healthy, fertile soil. And if you take a system where you're losing something faster than you're making it, so if you're eroding soil faster than you're rebuilding that soil, you're literally running out of it, drawing it down. The analogy I like to use is our bank accounts. If you have an income, you have expenses, and we have, at least at times in my life, I've had savings. And if you basically spend money faster than you make it for long enough, you burn through your savings. I know this for a fact. I've done it a few times. Soil is no different, and societies around the world have done this a few times, it turns out, as I go into and writing in the dirt book. But it takes a while, and that's one of the problems, is that the pace of soil erosion can be fairly slow. Other times, it's not so slow. This photograph from the Palouse in eastern Washington, my home state, illustrates why a geologist would look at the problem of plowing slopes, particularly steep slopes, as a really critical problem in terms of losing the soil off of a landscape. All those little channels that you see up there are not very big. They're no more than an inch or two deep. And we call them rills because you can plow right across them. You can erase them with a single pass of the plow. They're an agronomic nuisance. But what happens if they happen year after year after year? This is a winter wheat field in eastern Washington. You don't see any wheat, though, do you? What happened is that there was a rainstorm that happened after they had plowed, so you had runoff off a freshly plowed field. It carried away bits of soil. Farmer then planted through it, erased the rills, and if this happens year after year, it can really add up, as this photograph illustrates. It's another picture from the Palouse over in eastern Washington, and it was taken by Vern Kaiser back in 1961, and it illustrates how those little rills, if they form year after year on freshly plowed fields, can really add up. So that fence in the upper right-hand corner is the fence that the farmer built around his water cistern back in 1911 when the land was up at that upper orange line. Now, why did he put a fence around his water cistern? He didn't want to plow over his own water supply each year. That would be sort of annoying and expensive. So he put a fence up, and that defined the edge of this field. And the only thing that happened on this field for the next 50 years, between the time that the grasses were first broken and the photograph was taken, is it was in a wheat fallow rotation, annually plowed, and the plow, since it had a slope, would be pushing soil downslope little by little with each pass of the plow, and those rills would form and carry away more soil. And so between 1911 and 1961, that cliff formed. And so how big a deal was that? Well, I'm going to walk over and point to something on the screen that's a little hard to do otherwise, but there's a little black mark. It goes from here to here. That's a 1 foot increment on a survey rod, a stadia rod. And if that's 1 foot, that cliff is 5 feet tall. That's 5 feet of soil loss in 50 years. That's about a foot every decade, an inch a year. There's nowhere on earth that nature forms soil at that pace. This illustrates the fundamental problem with plow-based agriculture that has affected societies around the world. It can lead to soil erosion far faster than nature rebuilds the soil. Now, you should also be sitting there thinking, well, isn't that a pretty extreme example? And of course it is. That's why I use it. But how typical is it? You know, soil's eroding off at an inch a year. Well, you can find other examples of places from around the world where this has happened. But let's go and look at the problem not just on a single field in eastern Washington, but let's look at an example from the eastern United States, the eastern seaboard of the United States. This map shows you the magnitude of historical soil erosion in the Piedmont region, the region that stretches from Virginia up there in the upper right down to Alabama in the lower left. And Bob Mead, I think it was, that put this map together back in the 1980s, looking at what that magnitude was. And that gray noodle in the middle is the Piedmont, the upland country, the hill country between the coastal plain and the Appalachians. Why do you study that area? Well, it's the upland area that would be vulnerable to erosion. And you'll notice that that legend over there shows that 4 to 10 inches of soil have been eroded across this entire region in roughly the 200 years since the introduction of plows to the region. Some places had more than 10 inches erosion, all those black zones. How big a deal is that magnitude of soil loss? Well, if you go back and you read the original journals from the plantation owners that were first plowing these areas and planting, they only had about 6 to 12 inches of rich, fertile black earth above their subsoil. Their topsoil was about 6 inches to a foot thick. In other words, we've eroded off anywhere between about a third to all of the topsoil across a region that was once the breadbasket of the original American colonies. And we did it in just a few hundred years. Kind of puts into perspective what the Greeks could have done with a 1,000-year run at southern Greece, or what the Romans could have done with an 800-year run at central Italy. Has anyone ever been to the ancient port of Rome, Ostia? It's nowhere near the coast. You stand there and you look for the ocean, and you can't find it. Why not? Because the soils on the slopes of central Italy have been washed down and built the coast out into the Mediterranean far enough that you have to drive for a while to get from the port of Rome to the Mediterranean Sea. That was repeated at, all around the Middle East. And it starts to put into perspective the idea that the wholesale loss of the soil from the result of tillage, of plow-based agriculture over generations, could really add up to something that could damage the land. Now, I got approached a few years back by a television program called NOVA that is a PBS science program. They were doing a 3-part episode on the geologic evolution of North America. And I got a call as they were getting near the end of production. And they said they realized that they'd kind of left something out of the program, and they were realizing they needed to fill it in. And so was there anything that I might be able to suggest they could do to tell the story of soil in North America in 3 or 4 minutes or less? Because that was what the time slot that was left, sort of one segment. And I suggested, well, let's go to one of those places on that gray noodle from the map I was just showing you, and let's look at the soil there in what is a modern tobacco plantation field as an analog for what was happening in early tobacco plantation fields. And we put out a white tablecloth and took a shovel, one of the most useful tools on a farm, and went out and dug a sample of soil, the one on the right, out of the modern tobacco field. And then I went into the forest next door that had been abandoned as a farm about 100, 120 years earlier, and where the native forest had just grown back. And I took the shovel and I got another one and I put the one on the left, right next to it, on the white tablecloth. And why the white tablecloth? Well, it was television. It had to show up. And you had to make it a little dramatic. See any difference between those soils? Which one would you rather be farming? The one that looks like khaki beach sand that you could have scooped up off the California coast? Or the one on the left that still has a lot of organic matter and looks like chocolate? It's a big difference. And it also illustrates that one of the problems with the agriculture that has been practiced in many places around the world now for the last century or so is that it's not just soil degradation is not just a problem of losing the topsoil. It's a question of turning the stuff on the left into the stuff on the right, of changing the organic matter content, of losing the carbon in the soil. One estimate that was published in 1978 at that time found that about a third of the carbon that had been added to the atmosphere since the Industrial Revolution didn't come from fossil fuels. It came from plowing up the Great Plains, from plowing up areas of Eastern Europe, from plowing up parts of China, from degrading the organic matter in the world's topsoil. So soil degradation can include both the degradation of organic matter and the physical loss of the soil itself. But what I've shown you so far is kind of anecdotal evidence. When we look back at ancient civilizations, we don't have data from Roman times. We have 4 books on Roman agriculture, and I describe what they go through in writing the Dirt Book. There's a very interesting evolution of farming in the Roman world from small-scale polycultural family farms to large-scale, we might call them industrial for that time, monocultures that completely degraded their land. There's a great parallel with what happened in North America. But I'll leave, you can read all about that in the Dirt Book, but the point being that we don't have data from Greek times, from Roman times. There weren't scientists measuring things and writing them in journals. And so to put the story together for ancient societies, you have to triangulate through the state of the land, through some archaeology, and I'm a scientist, I wanted some data. So I wanted to test the idea of whether or not soil loss from tillage, from plow-based farming practices, could actually add up to enough to help explain the wholesale loss of the soil from regions around the ancient world, let alone the American southeast, as I was just showing you. So I went to the library for about a month when my grad students were all out in the field measuring their own things for their theses, and I gathered all the data that I could find on rates of soil erosion, and also rate off of agricultural fields, but also soil erosion off of native vegetation, long-term rates of soil building, and tried to compare them all. And what I came up with is I found about 1,400 different studies that I gathered data out of. And why did I stop at 1,400? Not because there's not more data that could be brought in, but I just ran out of time. And I've summarized that whole thing in this one table. I'm not going to show you a whole lot of data tonight, but if you're interested in the data behind this and some of the other things I'll be arguing a little later, there's papers in the scientific literature that illustrate that. The one behind this is in the Proceedings of the National Academy of Sciences from 2007. You can just Google my name and soil erosion, you'll go right to it with PNAS. What it shows you is on the left are different types of measurements. So the kinds of things that I was measuring. The numbers on the right are the average values, the median values. So half the values I found were smaller, half the values were higher. So that value in the middle is the one I'm showing you. And the numbers in parentheses over there on the left, those are the number of peer-reviewed academic studies that I averaged to give you the number on the right, just to give you a feel for how much work was involved. And why, don't bother trying to repeat this if you're a student, just steal the spreadsheet I published in PNAS and update it or use the data. You don't have to spend a month in the library to repeat it. And if you do that, send me the new spreadsheet, please. So what's the point of this? That red number up there on the top, that's the average rate at which I found that the world's conventional tilled soils were eroding off of farms worldwide, about 1.5 millimeters a year. That's not a huge number, right? You could stand around all day watching that happen. Your fingernails grow faster than that. The San Andreas Fault moves 10 times faster than that. And I've yet to see it move. And the buzz is gone, all right. The problem, of course, with agriculture is the difference between that red number at the top and the blue numbers below. Because that red number, 1.5 millimeters a year, you could lose an inch of topsoil in 20 years. Look at that number for soil production. That's how fast nature builds soils. 0.02 millimeters per year, a fraction of a millimeter a year. It takes centuries for nature to build that same inch of soil that conventional farming can lose in decades. That's the imbalance. Kind of backs up the argument I was making earlier based on anecdotal and archaeological considerations. But let's look at the rate of erosion under native vegetation and erosion, long-term geological erosion. They're kind of the same scale of those blue numbers, fractions of a millimeter a year. That's kind of reassuring because one of our primary observations around the world is that the Earth is covered with soil. And so if this long-term soil erosion rate under natural systems was much greater than soil building, we would be living on a bare bedrock planet. And if rates of soil production were much higher than rates of soil erosion over the long run, we'd have huge piles of soil, and soil erosion wouldn't be a problem. As it is, we have about a 1 to 3 feet of soil on most hillside soils around the world. If you can consult the UN Global Soil Database, they'll back that point up, because that's where I found the number. The problem, obviously, is the difference between those blue numbers on the bottom and that red number on the top. The red number is 20 to 100 times higher than those blue numbers on the bottom. Now, there's one set of numbers I haven't mentioned yet, and that's where the good news lies. Those things are labeled no-till. What's no-till? That's farming without the plow. It's using a seed drill. It's using a no-till planter. We have new machines and technologies that allow us to actually plant without using the plow. And the erosion rates that have been measured off of fields that are managed with no-till farming are actually pretty close to long-term rates of natural soil building. Adopting no-till can pretty much solve the soil erosion problem. It may not solve the soil degradation problem. We'll get back to that in a few minutes. But the good news is that the good news is that the bad news isn't that we farm. It's how we farm, how we've been farming in society after society. There's ways that we can practice intensive agriculture without losing the soil, in other words. That is the good news. But so far, I've given you all the data that it takes for you to calculate for yourself what the average longevity of an agricultural civilization might be. It's a rough calculation, the kind of thing you can do on the back of a napkin to impress your professors. But if you take that net soil loss of about 1 millimeter a year, and I could argue for 1.5 millimeters, but just give me 1 millimeter a year, and you could erode that typical 0.5 meter to 1 meter, that 1 to 3 foot thick soil, in only about 500 to 1,000 years. And when you look back through the history of agricultural civilizations, as I did in researching that dirt book, what you find is that most agricultural civilizations lasted somewhere between about 500 and 1,500 years or so. Kind of right in that same ballpark, with some really important exceptions. And those exceptions are the civilizations that developed on major river floodplains. Places like along the Tigris and the Euphrates in the middle, in Iraq and Syria, in Mesopotamia. Places like the Nile in Egypt. Places like the Indus and the Tsangpo or the Brahmaputra in India. Places like the big rivers coming off of eastern Tibet flowing through lowland China. Those are the places where agriculture has been able to be maintained for thousands of years with methods that involve disturbing the soil and plowing the soil. So how did they get away with it if the argument that I've been presenting is right? Well, the answer is hiding in plain sight in that word floodplain. What happens on floodplains? It floods, deposition, deposits, exactly. If you have a river that's not hemmed in by levees, so it can actually flood and spread across its floodplain, it doesn't bring just water. That water is going to have silt and sand and stuff in it. And when that water leaves the fast-flowing river and spreads out across the floodplain, it slows down. And what does water full of sediment do when it slows down? The stuff settles. Now, remember that number of 1.5 millimeters a year of the average erosion rate from agricultural soils? How big is a grain of sand? 1 to 2 millimeters is sort of medium to coarse grained sand. In other words, all you have to do to completely offset the long-term degradation from plow-based agriculture is deposit a grain of sand every year. How often do most rivers flood? Every year. You can get away with plow-based farming on floodplains pretty well over the long run as long as you get the floods to bring the mineral elements back to the soil. Where you can't get away with it are on hillsides. And what happened in society and after society around the world are that farmers started off in floodplains because it's flat, relatively well-watered, easily worked ground, and they spread up into the hillsides as more people were fed by more people, more farmers were able to feed more people and the population grew. And once farming spread to the hillsides, you started eroding the soil off, and that started to create problems generations down the road. So this is where I actually try and start turning this story around, because by now you might be getting kind of depressed about where the backstory of civilization has been if you think about those slides I showed you at the start that suggest that we're kind of on the same track at a global scale to repeat this experiment. So is soil restoration possible? Could we actually reverse the historical pattern of land degradation that has so greatly influenced ancient societies? And if I had come up with the answer of no, I probably wouldn't be traveling around talking about it. I would have bought a very large barrel of my favorite scotch and retired to the basement. But as it is, I started to learn that we can actually turn this story around and do it remarkably fast. I started learning that in my own yard. And I started learning it from the gardening activity of my biologist wife, Anne Baclay, who wrote The Hidden Half of Nature with me. And our sort of story started when we bought a house in North Seattle, and it had a side yard. So the house we bought's over there on the right. It came with a side yard that was just a monocultural lawn. I like to call it an old-growth Seattle lawn. It had about 6 inches of tangled roots, 1 species of grass, and when we ripped that lawn off to start making the garden that Anne really wanted to have, and she'd been jonesing for when we'd been living in graduate student housing for years and then junior faculty places. We finally had a place of our own that she could garden to her heart's content. We ripped the lawn off, and we find that we have this incredibly rich, fertile black earth that North Seattle is so well known for. Yeah, no, you can see up there we don't have any. What we had was dirt. It looks a lot like that conventional tobacco field in North Carolina, doesn't it? It has about the same organic matter content, about 1% or so. It looks like khaki beach sand. In part, that's kind of what it was. It's ground up bits of Canada that were scraped off by a glacier, bulldozed south into the Puget Sound, deposited in meltwater streams, or beneath that glacier, and then run over by a mile-high wall of ice 3 times the height of the Space Needle. Turned it into nature's concrete. It was not really good soil. It was dirt. There was not a single worm living beneath that lawn when we pulled it off. We didn't see a single macroscopic life form. It was a biological desert. The grass was there and doing okay, but nothing else was. And notice our neighbor's place in the back. I think that gray peaked roof will come back in a few moments. But basically, this was seen as a really big problem mostly by Anne at the start, because I could go out in the backyard, throw a tennis ball, our dog would chase and get it, and it was fine. I could get the grad students over once a year to play croquet and have barbecues on the lawn, and that's kind of what I wanted out of a yard. That's not what Anne wanted out of a yard. She wanted a thriving garden. So she decided to go on what we called her organic matter crusade. She got her wheelbarrow painted up, courtesy of a local auto body shop that had the template for making things go fast, and we convinced the neighborhood arborists to, when they would chip up the trunk of a tree or a limb, chip it up, put it in our driveway. And we started mulching the yard. We started trying to get organic matter from wherever we could around North Seattle, from our neighborhood. So we would get wood chips and compost, up there in the left-hand corner. We started adding seashells to get a calcium component in that would break down slowly. That pile in the middle up at the top was stuff that you can get from the Seattle Zoo. It's called Zoo Doo, and it's made courtesy of the herbivores. And they have an annual lottery. I think it may actually be every 6 months or so, where you can enter the lottery, and if your number or name is selected, you can bring over a vehicle and load up as much Zoodoo as you want and take it home for whatever you want, but most people put it in their garden. So we entered and we won, and Anne borrowed my truck. I didn't know we'd entered, and I was told we won the Zoodoo lottery, and I was like, what's that? She was like, can I borrow your truck? Next thing I knew, a truckload of Zoodoo arrives, and it ends up getting distributed around the yard, and it's deemed the best compost that we have access to. So we entered again. Or I should say she entered again, and we won. And so we got more Zoodoo, and then we entered again, and we won. And I came away sort of thinking that, hey, I guess you always win the Zoodoo lottery, because they kind of need to get rid of the stuff. We raked up our neighbors' leaves. You could be impressed with how friendly neighbors can be when you show up with your wheelbarrow and say, can we rake up your leaves and take them back to our place? They're like, sure, take it. And what they didn't realize is that they were giving us wonderful fertilizer for free. We still have a neighbor next door whose trees are kind of stunted relative to ours and whose garden is not as nice as Anne's garden, who's donated a whole bunch of leaves at one time. And she religiously picks up all the little leaves and cleans up her soil so that it looks sort of nice, not realizing that those trees are shedding those leaves to feed their roots. There's a point to all that organic matter that's being dropped on the land. And so we got all the kinds of organic matter that we could find. And we also started composting our kitchen scraps. Got a worm bin, started feeding the worms, and then she would take the effluent from the worm bin, put it into a 5-gallon bucket with an aquarium aerator, dump molasses in, and she's using the worm effluent to inoculate that sugar-rich broth with microbes. with microbial life and brewed up compost tea. Now, this is our introduction to thinking about what the role of beneficial microorganisms were in helping to build soil. And I was not terribly impressed, to be honest, at the start, sort of wondering how might this work. But after a few years of adding all this organic matter and inoculating the soil and the plants with a microbe-rich compost tea, we started to notice big changes in the soil in our yard. This photograph is taken about 3 or 4 years after we started with all that composting and mulching and soil souping, as the compost tea was called. And you'll notice that Anne's pruning shears are over there on the right-hand part of the screen. Notice across the bottom, we still have that glacial till. It's that khaki, hard, packed soil. And notice how the roots are coming down and they grow sideways above that. They're not growing down into that till. And you'll notice all the leaves and the mulch that's up there at the top. But what's in between? We have about 2 inches of halfway decent soil after about 4 years. Remember those rates that I was showing you, how fast nature builds soils? Centuries per inch? Anne was building 2 inches of soil in 5 years. That's almost getting up to that inch a year number that we were losing in the Palouse. Nature doesn't make the soil this fast, but Anne did. And there's farms around the world that I've seen that have. And I'm sure many gardens that have. There's a way to turn that stuff on the left, which is what we started with, into the stuff on the right. I know this because we did it. Or I should say, Anne did it, and I watched and wrote about it. And as did she. We had about a 1% organic matter when we started. Today, most of our yard is up to about 8 to 10% organic matter. We're up above that in the planting beds that got most of the worm compost. Not quite a 1% a year increase in organic matter in our yard, but pushing it, getting close. And this dramatic transformation of the yard is mostly due to the action of microbial life, of the bacteria and fungi in the soil, all the life that was in the soil breaking down that organic matter and reprocessing it into the raw materials for new life to take up, and the way station, if you will, along the way is soil organic matter. And it transformed the yard that we had from that old growth lawn into a booming place. You can't even see the neighbor's house today. And as nice as they are, I'm really happy to no longer be watching their kids grow up. They're welcome to do that in the privacy of their own home and yard. So what was going on? And I started looking into, how could we actually restore soil that fast when, if you look at the pace in all the journals and textbooks for how fast nature makes soil, we were making it far just off scale. And that took us to looking into a zone called the rhizosphere, which is literally Greek for zone around the roots of a plant. Rhizo is roots, sphere is zone, rhizosphere, zone around the roots of the plant. And it turns out to be one of the most life-rich areas on the planet. There's more microbes per centimeter of soil around the plant roots than there are almost anywhere else. You do a transect on soil life from away from a plant towards the root, you get more microbes towards the root. And it's not because there's all kinds of microbes running to attack the plants. It's not because of pests and pathogens. And how do we know that? Well, it turns out that something that Ann and I ran into when we were looking into all this really kind of surprised us. Is that plants, we know, take carbon dioxide from the atmosphere, combine it with water they pull from the soil, merge it through the process of photosynthesis to build the carbohydrate framework that builds their bodies. What we're not usually taught, and what we didn't really know up until a few decades ago, is that plants will also push out of their roots, will exude out of their roots, up to 30, 40, sometimes even more % of the stuff they fix through photosynthesis, they just push out into the soil in what's known as exudates, because they're being exuded out of their roots. Now, what are they exuding out of their roots? What are these exudates? Well, it turns out they're things like simple sugars, carbohydrates. They're proteins. And there's even a paper a year and a half ago or so that documented plants pushing lipids, fats, out of their roots and into the soils. What does that sound like? Carbs, proteins, and fats. It's dinner. It's food. Plants are pushing food out into the soil to feed the microbes. They're setting a buffet around their roots to encourage the growth of microorganisms in the rhizosphere. Now, why would they do that if they were feeding pests and pathogens? That would be an evolutionary dead end, right? That's a recipe for failure. But if you go back and you look at the first fossil plants we have on land, they have mycorrhizal fungi wrapped around their roots. in symbiotic relationships. These are partnerships that go back to the earliest days of life on land. And so how does that work? If you blow up the zone around the root of plants and you study it, you find that the rhizosphere is what Ann and I referred to as a biological bazaar, where microbes and plants are trading nutrients, metabolites, and exudates. So in other words, what happens is that big root coming down there in the middle, where the purple zone of the rhizosphere is around it, the little red things are all the bacteria living there, and the white things are mycorrhizal fungi connecting to the plant roots. Those plants are pushing exudates out into the soil, those black arrows, and that stuff doesn't make it very far. It only gets about 1 millimeter to 1 centimeter away from the root before something eats it. And what does everything do that eats something? It metabolizes it and then excretes the rest. What are the metabolites that some of those microorganisms are excreting into the soil? They're things, the one that blew Ann in my mind was when we found a paper that documented that some of those microorganisms were excreting as metabolites after consuming the exudates. They were making plant growth promoting hormones. Think about that for a minute. Bacteria making hormones to promote the growth of a plant, something in a completely different kingdom of life. Microorganisms are pretty incredible in terms of what they can consume, what they can break down, and what they make. They tend to specialize in certain chemical reactions, eating certain things, metabolizing them, and excreting other things. That's why we have wine and beer, for example. But we're not going to talk about that tonight. So basically what's going on are the plants are pushing out elements, nutrition into the soil to feed microorganisms that do things that help promote the health and growth of the plants. These are symbiotic relationships. There are also relationships that are vulnerable to disruption by both tillage, by plow-based agriculture, and intensive agrochemical use. How might that work? How might plow-based agriculture disrupt these relationships? Well, let's look at some hyphae, the root-like structures from mycorrhizal fungi in the soil. So these are the kind of fungi that will partner with a plant, and then their hyphae grow out into the soil and extract individual elements from mineral particles in the soil, things like phosphorus, for example. And they bring them back and they trade them to the plant for a cut of the photosynthetic harvest, for those sugary exudates. The plants are feeding the fungi. The fungi are acting as root extensions. Well, what happens if you plow the field up? You're going to be cutting all those little, chopping up those mycorrhizal networks. It'd be like somebody taking a D9 and going out to I-5 every year and just trenching right across the road and not putting any bridges in. It would completely disrupt commerce and traffic. That's what a plow does to what's happening in the soil, to those symbiotic relationships. And there's one other element that I'll address before moving on to the third book and sort of the global solutions aspect of this, and that is that some of the exudates that are pushed out by plants are done in response to disturbance by things like when an insect herbivore munches on the leaves of a plant, that plant can put out exudates into the soil that stimulate the growth of particular microorganisms that will either produce compounds that the plant takes back in to make the plant taste bad to that pathogen, or that in turn stimulate the plant to make a phytochemical, a plant-made compound, that can make the plant taste bad to that particular insect. The kinds of adaptations that are happening through the rhizosphere, the way that the plants are pushing out very specific compounds to nurture very specific microorganisms that help the plants in specific ways, are every bit as interesting and adaptively fine-tuned as what's going on above ground in the sort of the relationships we know between pollinators and flowers, for example. But we know about this because we can see them with our own senses. This stuff going on in the root zone, in the rhizosphere, has remained sort of off of our awareness for several reasons. First, it's underground. Out of sight, out of mind was not a cliche without a reason. And it's also because they're microscopic. We can't really see them. But those relationships are every bit as interesting. And it gives us a way to think about the diet that a plant eats and how to connect that to some of the problems that have come along with modern agriculture. When you think about through this lens of the rhizosphere and these symbiotic relationships in the soil with microorganisms, you think about feeding plants a fertilizer diet, as Ann and I call it, where you give them all the major elements they need. That NPK up there at the top, you get that big arrow, you get a lot of macronutrients to the plant, and you can grow large harvests and you can grow large plants that are very green and healthy looking, but they become what Ann and I call couch potato crops. They don't invest so much in their root network. And you can try this on a farm if you want, in terms of, I've got great pictures of the root systems that are different between same plants in the same fields with different fertilizer applications. And a plant that doesn't invest as much in its root network is not going to be putting out as many exudates. It's not going to be recruiting as many microbial partners. It's going to be light on the mineral micronutrients that those mycorrhizal fungi provide it, and light on the beneficial microbial metabolites that the community of organisms that those exudates feed provide it. In contrast, a plant grown in what Ann and I call the soil health diet, in healthy, fertile soil, is going to invest a lot more in its root network. It will be producing more exudates. It will have more beneficial microbial allies producing compounds that promote the health and growth of the plant. Very different ways to look at the plant diet. It's also a very simple way to explain why global pesticide sales went through the roof after global fertilizer sales went through the roof. Because we dismantled a plant's natural health system, its immune system and its defense systems for our major crops. This is the kind of thinking that led me into writing that third book, Growing a Revolution. What I wanted to do is to sort of look at the idea of whether or not you could take the ideas that work to restore fertility to our yard in sort of a little corner of North Seattle. Could those same ideas work at scale on farms around the world? Could they work on big farms? Could they work on subsistence farms? Would they work? And could you turn soil over there on the left into the soil on the right? In this example, the only difference is the application of compost and manure over 20 years. They're both no-till fields, but adding organic matter turned the stuff from khaki, sandy kind of color to a nice chocolate color. The difference is carbon. So I took 6 months off from my job at the University of Washington to research the book and basically visited farmers around the world who had already adopted practices that had restored fertility to their land. I didn't do a random sampling of the world's farmers. That would take the rest of the century, let alone my life. I went to visit people who had already done the thing I wanted to investigate how it could be done, people who had restored fertility to their land. And I asked them what they did. I told their stories, and I dug holes and compared their soil to their neighbor's soil. And searched for common principles that underlied these successful examples of farmers who had done that. And what I came away with is that farmers had adopted the principles of conservation agriculture, which I'll define for you in a moment, had restored their soil enough that they could match conventional crop yields with far less diesel use and far less agrochemical use, far less fertilizer and pesticide use. And as a result, they're growing as much and spending less. They were more profitable than their conventional neighbors. This is when I started to become an optimist. So what were those principles of conservation agriculture? They're really kind of simple. There's 3 ideas. They boil down to the kind of things that would promote the beneficial life in the soil, those organisms in the rhizosphere of our crops. And those principles, which is why all the microbes are on the screen up there. And those 3 principles are minimize this soil disturbance, or no disturbance, which translates into no-till farming or direct planting of seeds. Maintain a permanent ground cover, which translates into keeping cover crops on the ground. Don't let the soil be bare and vulnerable to wind or rain. And adopt more diverse crop rotations. Grow more than 1 or 2 things in a field. Have 4, 5, 6 or more different crops grown either in a rotation or in the fields all at once, as I'll show you in a minute. These 3 principles were the common things that all the farmers that I visited who were successful at rebuilding their soil remarkably fast had done. Some of them adopted some other things that I'll talk about as well, but those were the commonalities. And I'm going to introduce you to 4 farmers briefly, tell you a little bit about their story before wrapping up with the big picture. This is Dwayne Beck. He runs the Dakota Lakes Research Farm outside of Pierre, South Dakota. It's in conjunction with South Dakota State University. And you'll notice that there's no bare soil in his fields. He's got cover crops planted through the remains of the previous crops, and you don't see any bare earth. What he did is, well, I should tell you, why did I go visit him? Afterwards, if you look at the cover of my dirt book, there's a picture of farm implements in a car, one of those Dust Bowl era pictures of the dust-bearing farm implements back from that era. It was taken in his neighborhood. He was in ground zero for some of the worst effects of the Dust Bowl in South Dakota. And I wanted to see his farm because I saw him give a talk at a conference I was speaking at, and I was really impressed with what he was doing. And I said, I've got to go visit this guy. He took me on a several hundred-mile drive around his region when I first arrived, and we saw 3 plowed fields in a day during plowing season. The farmers in his region have almost walked away from the plow. They've almost all gone to no-till. And Dwayne had a big role in that transition. On his experimental farm, he was trying to look at how to adopt no-till practices. They then moved into cover cropping, and they started to diversify their rotations to more complex rotations. And as a result, they reduced their diesel, fertilizer, and pesticide use by more than half, in some cases up to 80–90%, not the diesel, the other things, which resulted in huge savings. And what happened to their crop yields? Well, you can look at the numbers. Their traditional yields for soybeans, they went up when they adopted their complex rotations and the full 3 principles of conservation agriculture. Their corn yields also went up. In other words, they were able to rebuild the health of their soil enough that they could so reduce their agrochemical use and raise their crop yields that they were much more profitable after the transition. This is why those ideas caught on and spread to the point where I only saw 3 plowed fields in the tour of his region. They worked. So when I left, I asked Wayne whether or not the kind of practices that he was using would work for subsistence farmers in Africa, because that's where the problem of feeding the world for the next 100 years really lies. That's where the population growth is expected. And Dwayne said, don't talk to me about that. I'm a farmer in South Dakota. They're using, some of these farms are 20,000 acres. These things were working at scale. And I wanted to know what about the small scale? So he suggested I go and visit this gentleman here, Kofi Boa, who runs the Center for No-Till Research in Kumasi, Ghana, in equatorial West Africa. And Kofi was very generous with his time, took me around to show me how the practices that he was teaching farmers in his region to adopt. And when I got out of the truck and saw his Got Soil, Get Dirt hat, I knew that this was a kindred spirit. He's working with farmers for whom the average size of a farm would be smaller than the room that we're all sitting in now. These are not large farms. These are small-scale subsistence farms. And they're getting diversity into their practices, not by so much by rotating crops, although some of them are doing that, but by growing multiple different crops, a diversity of crops in the fields all at once. That field over there on the left has plantains and peppers and several understory things. There are up to 6 to 8 different fields and crops in some of their fields. And what Kofi had done is he'd taken his people, he taught the people in his village to transition from their traditional slash and burn agriculture, where you clear a little piece of forest, burn it, harvest those nutrients from the ashes in effect through your crop, and then you farm it for a couple years, and then you move on to clearing a new piece of forest. You let the forest grow back for 20 or 30 years before you go back to the first spot. Well, what happens when your population gets big enough that you have to farm the same land year after year? You burn it year after year, you drive your organic matter down to close to 1%, and in the tropics, that's an agronomic disaster. What Kofi had done by teaching his people to go to no-till with cover crops, and with their diversity of crops, is they basically shut erosion off, which was a big problem under slash and burn. But notice what happened to their crop yields. Their corn yield tripled, their cowpea yield doubled. And they did this without inputs, without fertilizers, without pesticides. They did it by changing how they think, the way they manage their land, by changing their practices, by stopping plowing, by planting cover crops, and going for very diverse rotations. And that increase in crop yields is as good as we got with the Green Revolution, which so emphasized the use of fertilizers and agrochemicals. But that didn't work for subsistence farmers like Kofi worked with for a very simple reason. They don't have money to buy fertilizer. They don't have money to buy GMO seeds. They don't have money to buy pesticides. What they have is intelligence and labor. And by thinking differently and working differently on their land, they were able to greatly increase their crop yields, which had a transformative effect on the economics of their village. The third farmer I'll talk about is David Brandt. He's a farmer near Carroll, Ohio. This gentleman here, he is a rancher, but you can't see his livestock. They're invisible. He's a microbe rancher. What he does is he sells corn, soybeans, and wheat on the North American commodity markets, the sort of the big conventional crops, but he grows diverse mixes of cover crops in between his cash crops. He'll grow up to 12 or more different species in the fields at once, and he does that to feed the microbes that are in the fields. He does that to bring mineral elements out of the soil into his cover crop. He then kills the cover crop, lets it rot. Those elements go back to the topsoil where his cash crop takes them up as fertilizer. And notice that his field is pretty green. Look at the field in the background. His neighbor's field, it looks kind of different color, doesn't it? It looks pretty yellow. Those are kind of sickly soybeans in the background, conventional soybeans that are being grown. And you see little bits of green around them in the neighboring field. Those are glyphosate-resistant weeds that have been sprayed 3 times this year. You cannot kill them. Those glyphosate-resistant weeds are a major yield drag on his neighbors because up to about a quarter of their fields are covered with those weeds that they can't kill, and they're not growing a cash crop there. David Brandt doesn't have any weeds, let alone glyphosate-resistant ones. He plants cover crops and kills them before they go to seed. He turns them into fertilizer. What's it do to the economics of his farm? He walked me through his neighbor's operation and his own operation. His neighbors were full tillage. 200 pounds of nitrogen per acre were applied, 2.5 quarts of Roundup or glyphosate were applied per acre. That cost them about $500 an acre and had a yield of 100 bushels an acre back in 2015 when I was visiting there. That resulted in a net loss of $100 per acre for growing corn that year. Even a geologist can tell you that that's a very bad business model. The harder you work, the more money you lose. And I looked into sort of whether this is generalizable, and there's a paper that came out about that same year, 2015, for Iowa, that documented that 24% of Iowa farmers growing corn lost more than $100 a bushel, $100 an acre, growing corn conventionally. Why? Because they were spending a lot on inputs and diesel, and they were getting so little for their harvest because they were so good, and their neighbors were so good at growing so much that it depressed the prices. This is the problem. This is part of what squeezed family farmers out of North America over the last 50 years, is that commodity prices are depressed because they're so good at growing food, but the methods they use to beat for that success are so expensive that they're squeezed in the middle. David Brandt's farm has been no-tilled for 44 years. He then adopted cover crops. He's been doing that for a while now, and he's doing these diverse cover crop mixes, those 3 principles of conservation agriculture. He's not tilling, so he saves on diesel straight out of the gate. He's only using 1/8 of the nitrogen and 1/5 of the Roundup as his conventional neighbors. That cost him $320 an acre. His corn yield was 80% higher than the county average, and he was making at $4 a bushel. When his neighbors were losing $100 an acre, David was making $400 an acre. Which farm would you rather have? I'd rather have the highly profitable one, as would he. This is another thing that helped turn me into an optimist. So what is it that made the difference? This shows you what David did to his soil from 1971 to 2014. The stuff over on the right looks a lot like those khaki soils I was showing you earlier. The stuff on the left looks a lot like what Ann did to our yard. It's that adding carbon back to the land that restores fertility and productivity to it. This is why transforming his soil from the stuff on the right to the stuff on the left is what made David Brandt's farm so profitable again. He brought the soil back to life and rejuvenated the farm. The last farmer I'll share with you is a guy named Gabe Brown. He is a rancher whose livestock you can actually see, as he probably is standing in front of here and some of his cattle. He calls himself a regenerative farmer because his philosophy is to regenerate the fertility of the land. He's about building soil health as the foundation for his farm. And he's doing things very similar to what David Brandt and the others were doing in terms of the principles of conservation agriculture, but Gabe was adding another element. He was bringing livestock back onto his land because he has a pasture operation and a cropping operation, and he'll bring his cows in to graze off the crop stubble and the cover crops that he grows in between his cash crops. And what this does is it basically is using the cattle as 4-legged mobile self-propelled methane digesters to produce bovine exudates, manure, that is accelerating the breakdown of his cover crops and turning them into forms that his crops can take back up quite readily. So he's accelerating the breakdown and cycling of the nutrients in his soil, and the chickens are there to eat the fly larvae that come along with those bovine exudates. What has it done to Gabe's soil? The one in his left hand, the dark black one, that's the best soil on his farm. It's had the most sort of attention, and it's this rich black earth. The soil on the right, that's his neighbor's organic farm. Yes, let's cross one off my list. What is that? Uh-oh. All right, now it's where you pay for making me not use my computer. So, oh, just close that. Okay, this is why I use a Mac, because this doesn't actually happen on Macs. Close. All right. But basically, this is what you can do when you don't use Mac. This is what a Mac does. The one on the left, that's a Mac. The one on the right's a PC. So what is the recipe? It's actually really simple. I mean, in terms of visiting all these people around the world, the common elements that were underpinning the people who had great success at restoring their soil, it was ditch the plow, cover up with plants, and grow diversity. That defines a philosophy of farming that is 180 degrees from the philosophy that underpinned conventional farming in the 20th century, where we relied on intensive tillage, intensive agrochemical use, and growing one or two crops, monocultures. This is what I'm arguing for here, is that if we think differently about the soil, if we think differently about farming, if we think differently about how we treat the land, we can actually restore fertility remarkably fast, in decades, not centuries. And decades ought to be policy relevant. And I just want to emphasize that I haven't talked about GMOs, I haven't talked about the different, these practices are not about the difference between organic farming and agrotech farming. It's about how we think about the soil. Because I visited some organic farmers who had rebuilt fertility of their land, and I visited conventional farmers who had done it. These principles can actually work in both systems. There's no reason not to adopt them across the board. And in fact, as we did that, I started teasing Gabe Brown and David Brandt that they were organic-ish farmers, that they were so able to reduce their agrochemical use that they really weren't all that different than organic farmers at the end of the day. Adopting these principles could help across the board. And what would it do? I think it could set the seeds for a new agricultural revolution. We've had 4 so far by my count. The first was the idea of farming in the first place, cultivating the land and tilling it. It was revolutionary, changed the course of human development. It allowed us to go from societies where 99% of the people were farmers to one where 1% of the people are farmers, which lets people like me write books. The second agricultural revolution was when we realized that taking care of the land, building soil, husbandry of the soil was actually really important, and it could involve things like planting legumes in our crop rotations, going to actually rotating crops, not growing the same thing year after year. This was discovered by societies around the world, and we're incorporating traditional farming practices. Of those 3 principles of conservation and agriculture, you'll notice that cover crops and crop rotations are not new ideas. These were traditional practices around the world. What's new is merging those with no-till, with not plowing. That is the revolutionary perspective that could help redefine the future of agriculture. And this quote from Leonardo, it's like how many other quotes from science from 500 years ago are as true today as they were 500 years ago? The third agricultural revolution was industrialization and mechanization that swept through the 19th and 20th centuries. No argument there, it transformed agriculture. The fourth, again, no argument, in the 20th century, the Green Revolution and the ongoing biotechnology revolution had a big effect on agriculture. I'm not here to debate the pros or cons of any of those, but what I am wanting to say is that I think we're at a pivotal point in terms of what we do next. Do we carry on in the same vein? Or do we think about the potential for a fifth agricultural revolution that prioritizes building soil health, that adopts the kind of principles or adopts practices that embrace the principles that I've been going over and that I've shown you examples of farmers who transformed their land from relatively infertile land to really fertile land in remarkably short times. This is the potential for what I think of as a soil health revolution, a fifth agricultural revolution, one that doesn't abandon modern technology, but embraces it, but uses it to prioritize building soil health as the foundation for the future of farming. What else would that do? Well, it would help us restore farm profitability. It would help us feed the world by maintaining crop yields as our fossil fuel inputs get more expensive later this century. It would put carbon back into the ground, which will help us with the climate problem, and it could help reduce environmental degradation due to all the off-site effects of things like nitrogen fertilizers, which we could wean ourselves, if not completely off, we could wean ourselves off at least half in ways that would benefit pollution as well. There's all kinds of benefits that could flow from restoring health to our soils. That's what Growing a Revolution is about. It's a very feasible thing, and I know that because I visited farmers who've already done it. It's not a theory. It's been done. There's inspiring examples hiding out there in plain sight all around the United States, all around the world. And I'll stop there. I'll encourage, I brought copies of all 3 of these books. If anyone would like to pick any up outside afterwards, I don't know whether we have time for questions, but if we don't, feel free to corner me afterwards and ask. And thank you all very much for coming.
One quick question, and if you shout it, and Dave, if you can repeat it.
Oh, yeah. So the question is, how did David Brandt take down his cover crops? Gabe Brown used his cattle. David Brandt doesn't have cattle, so how did he do it? He used several methods. His preferred one most of the time was a crop roller, a roller crimper. So it was basically a device that's like a steamroller that has metal chevrons on it that he puts on the front of his no-till planter. So when he's taking down his cover crop, he basically rolls it down, turns it into mulch, and plants right through it. Sometimes, though, he uses herbicide. This is why he's an organic-ish farmer rather than an organic farmer. Although he's going more and more towards just using the roller crimper from when I last talked to him.
So I would like to thank all of you for coming out tonight. I'd also like you, if you didn't have an opportunity to sign the sheet, to stop by one of those tables, sign the sheet. Our 4 guests in the lobby are going to be out there for a little while afterwards, so please feel free to go visit them. I'm going to have you leave Dave alone so that he can go out by the table by his books, and you may ask him questions out there. But most importantly, thank you all for participating and showing up tonight. Hopefully I'll see you on May 19th.